Hey everyone, and welcome to this explainer. Today, we're going to look at what happens to the fundamental rules of physics when things get, well, crowded. We're taking the nice, clean rules of basic electrical forces and throwing them headfirst into a room full of multiple, interacting particles. Should be a lot of fun, right? Okay, so here's our roadmap for today's deep dive. We'll start by going beyond two charges, then we'll unpack the principle of superposition and move on to adding up the vectors. After that, we'll tackle the equilateral triangle problem and wrap it all up with the power of symmetry. Okay, let's dive into this. Part 1, Beyond Two Charges and the Limitations of Coulomb's Law. So, Coulomb's law is brilliant, isn't it? It perfectly maps out the mutual electric force between two interacting charges. But you've got to wonder, what happens when there are several charges around? If we have just one single charge, let's call it Q1, and it's completely surrounded by a whole crowd of stationary charges, Q2, Q3, all the way up to some number n, Coulomb's law on its own just doesn't cut it anymore. We desperately need a new way to calculate the force acting on Q1 in this super crowded environment. Which brings us to part 2, the principle of superposition, otherwise known as the elegant solution. So here is the formal definition. The principle of superposition states that the force on any charge due to a number of other charges is the vector sum of all the forces on that charge due to the other charges taken one at a time. Now, that absolutely crucial phrase there is taken one at a time. You see, charges don't really care about the whole crowd at once. They deal with their neighbors completely individually. To put it simply, individual forces are entirely unaffected by the presence of other charges. Think of it like this. If you're having an intense one-on-one conversation with a friend and a third person walks into the room, the actual physical interaction you're having with your friend doesn't just magically vanish, right? It's the same with physics. If you introduce a third charge, Q3, into a system, that fundamental connection between Q1 and Q2 isn't erased or interrupted. It exists exactly as it would if they were completely isolated in a vacuum. Moving right along to section 3, adding up the vectors and the mechanical connection. Now, you might be wondering, do these invisible electrical forces play by some weird, complex quantum rules? Well, actually, no. Experimentally, it's been totally verified that electrostatic forces stack up and add together using the exact same rules as everyday mechanical forces. Yep, they both rely on the parallelogram law of addition. So, combining the physical push of two external forces on an everyday object uses the exact same mathematical method as combining the microscopic forces of charges. Pretty cool, right? So, how do we actually do it? Let's break down that intimidating mathematical summation formula into simple physical steps. It's like building a toolkit. First, you just use Coulomb's law to find the force between Q1 and Q2. Easy. Then you isolate Q1 and Q3 and find that specific force vector. And then, well, you just repeat this for all n charges in the entire system. Finally, you combine them all using standard vector addition to find your grand total. It's basically just drawing arrows pointing in space. I really want to pause for a second to highlight the sheer magnitude of this statement from our source material. All of electrostatics is basically a consequence of Coulomb's law and the superposition principle. I mean, wow. Just think about that. These two incredibly simple building blocks literally create the entire foundation of electrostatic theory. It's the whole shebang. All right, let's amp up the energy a bit for our boss fight, Section 4, the equilateral triangle problem. This is where we're putting all of our new tools to the test. I want you to picture this in your head. Imagine a perfectly symmetrical equilateral triangle. At each of the 3 outer corners, the vertices, we lock down identical charges, which we'll call lowercase q. Then, right in the dead center, the centroid, we drop in a brand new charge, uppercase Q. So the big question is, what is the total force acting on that central charge Q that's trapped evenly between the other 3? Let's walk through the step-by-step vector addition. It's kind of like a multi-directional tug-of-war. The top charge at point A pushes down on our center charge Q along line AO, and that gives us force F1. At the same time, the bottom 2 corners B and C push up and inward along lines BO and CO, creating forces F2 and F3. Now, if we use that parallelogram law we just talked about, F2 and F3 merge to form a single upward push along line OA. And here's the magic. This combined upward push exactly equals the downward push from the top. They perfectly, flawlessly fight each other and cancel out. The result? 0.
The resultant vector unit is literally zero, because all the charges at the corners are equal and the distance to the center is perfectly equal. All those complex individual forces just balance out to nothing. Our charge Q, just sitting there in the middle, feels absolutely no net force whatsoever. It's basically chilling in the eye of an electrostatic hurricane.
And that brings us beautifully into our final part, Section 5, the power of symmetry, which is essentially the ultimate cheat code in physics. You know, to solve that triangle problem, we didn't actually need to crunch all those numbers and vectors. Actually, scratch that, we didn't need the math at all. It is clear just by symmetry that the three forces will sum to zero. Spotting a beautifully symmetrical system with identical charges is a massive shortcut. When the geometry is perfectly balanced, the physical forces just naturally balance out to zero.
But before we wrap up this explainer, I want to leave you with a final kinda mind-bending thought experiment from the source text. Suppose the resultant force in the middle of that triangle was not zero, but actually pointed in a specific direction. Now consider what would happen if you rotated that entire equilateral triangle exactly 60 degrees. The setup would look absolutely identical, right? Yet the force would suddenly have to point a completely different way. So how do you resolve that paradox? Think about that as you mentally spin the triangle to see the physics in action. Thanks for joining me.